Hello everyone, today we're going to compute lines on surfaces. Let's get started. Let's start with a basic observation that we will need. This will be about counting points and how magma or in general computer algebra systems count points on schemes. I'm going to work with the rational number field and I'll call it QQ. Let P1 be the projective line. So you can define this in one of many ways, but here's one function. So this now will give us a projective space of dimension 1 over the field of rational numbers. And x, y here are the homogeneous coordinate functions on P1. Another way to say it would have been to construct the proj of a polynomial ring, let's say qxy. So you cannot write qxy to define the polynomial ring, but you could first define the polynomial ring and then write proj, and you would get this same object. Inside of here, I want to construct the following polynomial, x squared plus y squared. So its zero set is what I will be working with, and its zero set is 1i and 1 minus I. So that is what I'm thinking of, and I could express this pair of points on the projective line with the polynomial f. So I could say x scheme in P1 defined by the polynomial f, and this will be the pair of points corresponding to f. Let's just make sure that we are doing the right thing. I'm going to check if the dimension of x is 0, because x should be a pair of points. And let's also count the number of points with the function degree. And let's see what this gives us right now. Just copying it into magma, and it says the dimension of x is indeed 0 and the degree of x is 2. That's in line with what I expected. I expected 2 points, so 0-dimensional objects, and 2 is this 2. On the other hand, if you were to write points in x, so you can check what points does with the question mark, but if you were to write points in x, you would expect to see the points defined by x, but instead you get the following. You get the empty set, empty sequence, whatever. And this tells you that we're now paying the price of working over the rational numbers. What the function points does is that it checks if x has any points defined over your base field, q in this case. And of course there are no q points on x. Nevertheless, the degree x command does some algebra that actually gives you is about the algebraic closure of your base field. So that's what algebraic manipulations tend to give. And when you're working with an algebraically closed of characteristic 0, you might as well work over the complex numbers. So you can always change to either a simple extension of q such that you see these points, q bar, or complex numbers. And that's what these algebraic operations, dimension and degree, see, but not points. That remembers your base field. And if you wanted to see all the other points, you could say points over splitting field. Now it says the points are of the form R11 and R21 in P1, the projective line. And as you can see, these two are roots of -1. This representation is not optimized. If you read about points over splitting field, you'll see that this is the case. And here, for example, you don't see that R1 should be minus R2. Now let's talk about another aspect of finding points, which is the danger of using the command degree. Let's take x to be the scheme defined in P1 again, but this time I'm not going to use f, I'm going to use f squared. In this case, if I were to just copy these two here, so I'm going to check dimension and degree and then see what points there are. Let's copy paste. This time the dimension is 0 still, degree is 4, and there are no points again. So what has changed is that the degree is now 4, although obviously the number of points has not changed. So if you were to say points over splitting field and maybe count number of points over the splitting field, then you get 2. And one way to think about these is that f squared is kind of points with a tangent direction, and as a scheme it has a more complicated structure, therefore its degree is 4. But in terms of finding points over fields, then the number of points do not change. What you can do when you are interested in the number of points, you could of course compute the points over the splitting field and then put this hashtag number in front of there to count the number of points. But this would be absurdly expensive. Finding the points is much more expensive than counting them. The other option is to say, is x reduced? So the problem here was x was not reduced. and you can check this with the command is reduced. When x is reduced, then you can just ask for the degree and you'd be good. When it's not reduced, you can say the reduced subscheme of x. It now gives you a description of this subscheme, and you will see that it recovered f. And now we could have asked for the degree of the reduced subscheme, and we would get the correct number of points. So the second part of computing reductions we will not explicitly use, because we will be operating in a setting where geometry dictates that the results we get will automatically be reduced. The point sets that we compute will automatically be reduced. On the other hand, this is very important when you're doing your own thing and you don't know a priori that the schemes you construct will be reduced points, and you want to apply the map degree. Then you should use reduced subscheme. Now let's talk a little bit about surfaces, and I want to talk about surfaces in P3. So I'm going to construct the space P3 by x with coordinates x, y, z, w. So we constructed the projective space over the rational numbers of dimension 3 and the coordinate functions x, y, z, w. What you can do when you want to reference the polynomial ring generated by the coordinate functions, you can say the coordinate ring of a scheme, and it will give you what you need. So I've assigned it to R now. Let's check this is doing what we think it should be doing. So R is indeed polynomial ring of rank 4 over a rational field with variables x, y, z, w. Conversely, I could have defined the polynomial ring and then set P3 to be proj of R. For example, this gives me a projective space of dimension 3. Let's construct a surface of some degree. Let's say our degree today will be 3. Although everything I'm going to do will work over arbitrary degrees. If you're writing your own code, you should just change this d to be some other number. In fact, I encourage you to try it as you're listening along. Now, the second thing I'm going to do is to generate a random polynomial. So what's happening here is that first I'm generating the set or sequence of monomials of degree d in R, homogeneous monomials of degree d. And amongst this, I'm running through all monomials. I call them m. I multiply each with a random integer from 1 through n, and then I sum them up to generate my polynomial. This is what f looks like now. And now let's consider its zero locus inside of P3. So I'm just going to write the same kind of notation, maybe I call it S. This will be scheme in P3 defined by F. And now we can ask the usual questions. So what is the dimension of S? What is the degree of S? Another interesting question is this thing non-singular? Okay, so let's look at these answers. It says the dimension of S is 2. So once again, you can think of this not as the set of Q points at all. These things are thinking over the algebraic closed fields. So either consider it over Q bar, or even better, you can think over the complex numbers. So this is saying that S is a complex manifold, and I can call it a manifold because it is non-singular, so it's smooth. And the degree of S is the degree D that I've chosen. So the degree of the polynomial f will be the degree of the scheme in this case. Okay, so this is the basic information about a surface. And now, since this is a 4-dimensional real manifold or a 2-dimensional complex manifold, hence a complex surface, so we can view it like this. When I want to ask about lines inside of this surface, it's kind of a non-trivial question, and especially when the degree is higher. Let's now turn to this. What I want to do now is to first generate a line and then check if this line lies inside my surface, and if not, maybe realize what the intersection points might be. So let's make it simple. I'm going to generate a matrix . So this is a 2x4 matrix, and a 2x4 matrix, as we discussed last week, defines a line inside of P3. Now I want to parameterize this line, and so I define the following coordinate ring. So this is a polynomial ring with 2 variables. I call these variables uv. I refer to the polynomial ring with the capital U, and I have in mind that this is the coordinate ring of a P1. And this P1, I would like it to parameterize my line inside of P3 defined by this 2, 5, 4 matrix. The way you can do this is to say U times first row here and V times the second row here, and then sum them up. So let's do this now. So I've created a row matrix UV, and now I'm going to multiply UV with L, but this will not work by itself. Let's see. This Magma is very pedantic about what you are allowed to do. So it mathematically doesn't make sense because UV is a matrix over some other ring than L. Therefore, this operation to Magma does not make sense. Let's see what it says. You see it says these two matrices have incompatible coefficient rings. And what we need to do is to coerce the second matrix into the coefficient ring of the first matrix. So this is the notation. So you take a matrix, for example, then change its base ring to U. So this is where UV lives, and now this product makes sense. Very good. You see now I have a 1 by 4 matrix. The coordinates are U plus 5V, 2U plus 6V, this and that. Since I have 4 coordinates, I'm really thinking of something in P3, and the UVs are variables. So I'm parameterizing something in P3, and clearly this is a line in P3 defined by my 2 by 4 matrix. What I want to do is to see how the zero locus of my surface defined by F interacts with this line here. Let's first define. So let's change this first of all from a matrix to a sequence to the set of coordinates if you want. That's what you get. And now what I want to do, remember I have a polynomial f. I want to pull back f to u, or equivalently to evaluate f at these 4 coordinates. Since the x coordinate along this line has this form and the y coordinate along the line has this form, I can just plug in for x the first coordinate, for y the second coordinate, and so on. And then this will give me the pullback of the polynomial f to the projective line. And this is the notation. You say evaluate a polynomial and a sequence with the right number of entries. So 4 entries is needed in this case. And you see I get a degree 3 polynomial, a bivariate polynomial. And since this is homogeneous, a homogeneous bivariate polynomial should really be viewed as a univariate polynomial with a single variable. So I get a cubic. And of course, a cubic has 3 roots, and the locus when f equals 0 intersects this line precisely when the pullback is 0. Therefore, I see that I have 3 points on my P1 that ends mapped to 3 points in the line inside of P3 that happen to lie inside of my cubic. And using this explicit polynomial, you can then find these coordinates precisely. But that's not what we're going to do. The main question that we're interested in is, does the line that I just created inside my surface? And of course, it's not in my surface, because if that was the case, the pullback of f would be identically 0 on the line. So if the line lies inside the 0 locus of f, the pullback of f should be identically 0, whereas this pullback is clearly not identically 0. And so we see what we are supposed to be doing. We should check whether these coefficients are 0 to decide if a line is inside our surface.